Welcome to the Walton Pi. This is the second installment in my AP Precalculus series, where we are going over all the topics that are covered on the AP Precalculus AP exam. So this one is going to cover sections 1.3 and 1.4, which talk about rates of change. In linear functions, such as y equals 7x plus 4, the average rate of change over any interval is constant. And we say that the rate of change at every point, that's the slope of the line. So in our example, y equals 7x plus 4, the slope is 7. So that means that every average rate of change and every rate of change at a point is going to be 7. And since the rates of change of linear functions are constant, we say that the rate of change is changing is 0. This means that linear functions have no concavity. They're not concave up, they're not concave down. In quadratic functions, such as y equals x squared plus 2x minus 3, the average rate of change over consecutive equal length intervals can be expressed as a linear function. So let's do an example. So if our intervals are 0, 1, 1, 2, 2, 3, ... then we can see that we are going to be able to figure out what's the average rate of change over each interval. So over the interval 0, 1, we find that the average rate of change is 3. Over the interval 1, 2, the average rate of change is 5. Over 2, 3, the average rate of change is 7, and so on. And then what we can then see is that then the average rate of change over n to n plus 1, that is 2n plus 3. Okay, so this means that for quadratic functions, the rate of change is changing is a constant. In this case, 2. So in our last example, we were looking at the average rates of change in consecutive equal length intervals. And the values of those average rates of change were increasing. Anytime that's occurring, where we have sufficiently small lengths of intervals, we say that the function is concave up. So remember, a function is concave up when the rate of change at points is increasing. This allows us to check if it's concave up, where we look at rates of change over intervals. So that makes it a little bit easier to compute. So you just have to do it with sufficiently small lengths. In our last example, those were lengths of 1. In other examples, you might need to be looking at lengths of 0.1 or 1s, but you don't want to be going too big, so 10s and 100s, those are going to be too big and you're going to be missing if it's actually concave up or not. So what we can do is we can approximate the instantaneous rate of change with small intervals, and that allows us to get an idea as to what the concavity of the function there is going to be. So we can also do a similar thing with concave down. So remember, a function is concave down when the rate of change at points is decreasing. So if we approximate the instantaneous rates of change with small intervals, we can get an idea as to the concavity of the function. So if the average rates of change are decreasing for consecutive sufficiently small lengthed intervals, then that means that the function is concave down in that region. So now we can expand this out to cover any type of polynomial. So a non-constant polynomial over x is a function whose analytical form is equivalent to this. P of x is a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus ... a2 x to the 2 plus a1 x to the 1 plus a0, where these are the requirements. N has to be a positive integer, every a sub something is a number, and a sub n is non-zero. The reason that we make a sub n be non-zero is just so that we can be able to say what's the very first term of the polynomial. We don't want to do 0x to the 100 plus 0x to the 99 plus ... plus 0x to the 4 plus 1x cubed. We want to just be able to just start at the first non-zero thing. And then what we're going to do is we say that n is going to be the degree of the polynomial. It's the highest power of x that shows up. And then a constant is just a polynomial function of degree 0. So let's look at some examples and look at what are the rates of change doing on this function. So here's our polynomial function. P of x is 0.07x to the 5th minus 0.35x to the 4 minus 0.21x cubed plus 1.5x squared plus x plus 2. And we see that we have this nice little graph. How would we graph this by hand? Very carefully by plotting a lot of points, but we are given this and we're trying to figure out what are the different rates of change that we have. So there are several places where the polynomial function is switching from increasing to decreasing or from decreasing to increasing. These are called local extrema or relative extrema. So local extremes, relative extremes, as places where we have maximums or minimums. And these are also going to be occurring at endpoints if the function's over an interval. For this particular function, we've highlighted where those are going to be. Now, a useful fact about polynomials is that between any two distinct real zeros of the polynomial, there's always at least one input value that corresponds to a local extreme. So between our first two zeros, which are at about -2 and a little bit past 3, there's going to be 3 input values that correspond to a local extreme. Now, it doesn't say that there's exactly one, it says there's at least one. We have no way of guessing how many there's going to be, at least right now. And so right now, all we know is there's at least one. When we graph it, we can see that there's 3, but there's at least one input value corresponding to a local extreme value. But then between the zeros around 3 and around 4, there's also another extreme value. And so that's what this theorem is telling us, is saying that between any two zeros of a polynomial, there's going to be at least one extreme value, or local extreme value. Now, this fact actually applies to all continuous functions, so it doesn't even have to be a polynomial. It just works for polynomials because polynomials are continuous functions. We can also be looking at the concavity of polynomials. So I've now highlighted the regions where the polynomial is concave up in purple, and then the white regions are where the polynomial is concave down. We say that points where the function switches concavity from either concave up or to concave down, those are called points of inflection. And so we have 3 of them here highlighted in those little circles there. Now, going back to our local extremes, they can either be local maximums or local minimums. It's a local maximum if it's a peak, and it's a local minimum if it's a valley. So if any of these local maximums are greater than all other outputs of the function, we call it the absolute maximum or the global maximum. Now, if any of these local minimums are less than all other outputs of the function, it's called the absolute or global minimum of the function. And again, we don't have any of those in this function. Now, not all functions have global maximums or minimums, as we've just seen. However, every polynomial of an even degree has either a global maximum or a global minimum. Now, our function p of x, that's a polynomial of degree 5. 5 is not even, so we are not guaranteed a global maximum or minimum. However, if we look at f of x is x squared plus 2x minus 3, that's a even degreed polynomial, x to the 2, okay? And so that has a global minimum at the point -1, -4. I hope this was helpful in understanding the different stuff that we, all the different terms that we use in talking about rates of change. If it was, please like and subscribe. I'm coming out with a different pre-calculus video every week for the 2023-2024 school year. I hope you have a great rest of your day. Good luck with all of your math. And if there's other topics that you would like to see me make videos on, please leave that in the comment section down below. I hope you have a great rest of your day and good luck with all of your math.